Well, now that we have functions of a complex variable, we'd like to talk about the properties of functions of a complex variable. And well, if you think back to calculus, the main ideas that you're really interested in calculus are differentiability and integrability. But the idea of the limit is underlying to these ideas, and it is typically covered in Calculus 1, and then, well, basically only revisited sporadically. In this course, it's going to be similar in the sense that most of what we're going to talk about in regards to limit and continuity will be in this presentation, but we're going to go a bit deeper than calculus. We're actually going to give a precise definition of the limit of a complex function at a point, which in fact is or can be translated also to the real numbers pretty much verbatim. The proofs that are involved will actually be important in this course in the sense that we want to understand why the results that we're quoting are true. And for this presentation specifically, we will make good friends with the triangular inequality, which in limit arguments is always one of the standard tools to be used. So let's get to it. Let's see. The idea for the limit, that doesn't change at all. The idea for the limit is always to attempt to answer the question, what happens when the input of a function gets close to a number at which the function cannot be evaluated? Okay, sometimes we'll also take limits at points where the function can be evaluated, but the motivation basically comes from functions of a variable h, say d of h, that are defined as this difference quotient f of z0 plus h minus f of z0 divided by h, which, if you go back all the way to calculus 1, is the definition of the derivative. The idea for the derivative is that we want to know what happens with these difference quotients as h gets small, and historically speaking, actually, the people who invented calculus, Leibniz and Newton, basically wanted to know what happens with these difference quotients as h is equal to 0. Nobody really knows what Newton really thought of as he invented the derivative. Leibniz was thinking about numbers that are incomparably small but not 0, which are abstract entities that are actually a whole lot more complicated than limits, and only, I think, close to 200 years after Leibniz and Newton, the idea of a limit, which finally put calculus on a solid formal foundation, was put forward by Weierstrass and Cauchy, depending on whether you want to listen to the Germans, who credit Weierstrass with the invention of the limit, or whether you want to listen to the French, who credit Cauchy with the invention of the limit. Okay, well, both these men obviously were brilliant, and I think there were a lot of parallel developments there, and I would have no problem crediting both of them with the idea. Okay, well, so the other part of when we're talking about limits is that limits can also help answer the question, what happens when the absolute value of the input gets large? Continuous functions are then functions for which limits are computed by plugging in the numbers. So those are limits where we take limits at points where the function can be evaluated and where the function behaves nicely. Well, unlike for functions on the real line where we can only approach from the left or from the right, because the complex numbers are two-dimensional, it's sensible to first consider the properties of the domain also, and so that's what we're going to start with. The main underlying definition, which we're going to talk about repeatedly, explicitly as well as implicitly, is the following. If you take a complex number z0 and you let epsilon be greater than 0, then the epsilon neighborhood of the point z0 is the set of all complex numbers z, so that the absolute value of z minus z0 is smaller than epsilon. So this is the set of all complex numbers that are closer than epsilon to our center point z0. So this is the formal way to encode closeness. If we've got a domain somewhere, got a number z0, well then if we put a small circle around that of radius epsilon, that is the epsilon neighborhood of z0. In analysis, typically, even though we're just saying epsilon is greater than 0, typically the connotation is epsilon is considered to be small. So these things are small circles around z0, and that means that we're really talking about points that are close to z0. So the idea is to encode closeness with epsilon neighborhoods, and we'll see in the definition of the limit, which we will talk about informally as well as formally, how this idea of an epsilon neighborhood allows us to talk more precisely about what it means for one number to be close to another number. Okay, well, let's consider z0 again. Let's let epsilon be greater than 0 again, and let's talk about the deleted epsilon neighborhood of z0, which is the set of all complex numbers so that z minus z0 absolute value is smaller than epsilon but greater than 0. So those are all numbers that are close to z0 but not equal to z0, which I'm trying to indicate here with this open circle. That is important because, as we remember from calculus, the idea for the limit talks about what happens near z0, but it doesn't care what happens at z0. So that's where we're interested in these deleted epsilon neighborhoods. Limits are considered on deleted epsilon neighborhoods, and that's because, yeah, just like I just said, the function is not defined near but not at a point z0. Sometimes it's also defined there, but we typically will not care what that value is unless we're talking about continuity. So we want to use the behavior in the deleted epsilon neighborhood to find out what happens at z0, or what we could make happen at z0 if the function is not defined there. Okay, now we continue talking about regions, and we're going to talk about a set S contained in Z repeatedly here, and we're just going to introduce some vocabulary. So a set S contained in Z. Well, a point Z0 in S is called an interior point if and only if S contains an epsilon neighborhood of Z0. So this is the element sign. That just means that the point is in the set. So again, we just talk about a generic domain, and z0 in this situation is an interior point because we can draw a little circle of radius epsilon around z0, and that whole disk is contained inside this domain. Now, a point that is not in S is called an exterior point if and only if there is an epsilon neighborhood of the point that contains no points of S. And so that basically means with the same generic picture, we would take a point that is exterior, and well, we call that thing z0, and we have a small circle around that point that doesn't intersect with the domain at all. Now you might think, well, okay, so an interior point and an exterior point, that's all there is. Well, it turns out that if a point is neither interior nor exterior, then that thing is called a boundary point. And that can't really happen, because basically z0 is a boundary point if and only if every neighborhood of z0 contains points that are in S and points that are not in S. So if we're looking at our generic domain, well, boundary point suggests that those things should be on that solid line here, and that's indeed where all the boundary points are. And the idea then for a boundary point z0 is that no matter how small a circle we draw around this thing, there will always be some points in S and some points outside of S that are inside that circle. So that's what it means to be a boundary point. A set then is called open if and only if it contains none of its boundary points. And typically I will indicate that by having a dotted boundary. That means we're interested in the region that is indicated inside that boundary, but the boundary itself is not a part of the whole thing. A set is called closed if and only if it contains all of its boundary points. That's usually indicated with a solid boundary line here. But then we have to remember sets are not like doors. I mean, a door is either open or closed. A set can be neither open nor closed, and you may want to think, well, how can that happen? And basically it can happen if a set contains part of its boundary but not all of its boundary. So if some part of the boundary is missing but other parts of the boundary are there, because then it's not open because these points here are not interior points, but at the same time they're not closed, because these points here that are not in the set are not exterior points. Okay, we keep considering sets. I think now we're going to talk about connectivity. Right, an open set is called connected. Technically, if you want to go deeper into topology, people would call it pathwise connected. If and only if from any point in S to any other point in S, there's a path, and sometimes we also would like to say just a polygonal path. Well, basically, let's take this standard picture again. Here's one point, here's another point. As long as I have a connecting path from every point to every other point, then that set is connected. And even though I'm only considering 2 points here, I think it's pretty obvious that no matter which 2 points I would choose inside this set, I would always be able to take a path from one point to any other point. The opposite of, okay, so C connects P and Q. Otherwise, the set is not pathwise connected, and that can also happen. Take this set as here. So this looks like 2 sets, but of course, just like I can form the union of 2 intervals that have some points in between them, I can form the union of 2 sets like these in the complex plane that are just somehow separated from each other. And of course, that doesn't look connected. And that's because if I take this point P here and this point Q over here, then even though I can try to draw a path from P to Q and even succeed in drawing that path, any connecting path from P to Q must leave the region, and that means this thing is not pathwise connected. Okay, we continue to consider sets S. What else do we have? Oh yeah, now there is some vocabulary that is specific to, well, complex analysis, or specific to the textbook that I'm using for this text, Churchill and Brown. But at least they define it. A domain is something that is non-empty, open, and connected. And they use that language very consistently, and we will use it consistently too. So basically, that is a set that is about as pretty as can be for the purposes of doing analysis. A domain that has some, none, or all of its boundary points included or attached to it, that's called a region. And then standard language, again, a set S is bounded if and only if it lies inside some circle, Z absolute value equals R. So if we take a set like this, well, if we can draw a large circle around that thing that contains all the points in the set, and that's happening here, then that set is considered bounded. Okay, and if S is not bounded, it's called unbounded. Can't draw a picture of that because, of course, unbounded stuff goes off to infinity, and that's rather hard to draw on a finite sheet of paper or a finite panel here. And finally, a point Z0 is called an accumulation point of S if and only if every deleted neighborhood of Z0 contains a point in S. I don't think we'll actually have to worry about those accumulation points too much, but I think I included them in here for completeness' sake. Okay, we're going to start talking about limits, but, and I mean, this is a long presentation because all of this really is logically connected, but if this was a lot of vocabulary for you, and if you just want to talk, want to do some homework problems on shapes of domains and the like, then go ahead, stop the presentation right here, and continue it later on. Okay, we continue with limits, and as you may recall from calculus, and if you don't recall it from calculus, I wouldn't blame you for it because you talk about it early on, but then for basically close to 3 terms, you don't revisit it anymore, or at least not in any serious fashion. The informal idea for the limit is that W0 is the limit of the function f at Z0 if and only if for all z that are sufficiently close to Z0, we have that f of z is close to W0. This definition here, as it's written, doesn't refer to complex numbers at all, except that we're using the notation that we want to use for complex functions. And so indeed, if you go back to your calculus text, this is verbatim, or as close to verbatim as possible, using different kinds of references. This is the definition of the limit of a function of a real variable also. The problem with this definition now is that we don't really know how to define what it means to be close to two numbers, and we also don't know what it means to say two things are sufficiently close to each other. Think of this in terms of scale. For someone who is working in celestial mechanics, the Earth is close to the Sun, and on galactic scales that is certainly the case, because the Earth is a whole lot closer to our Sun than any other star in the Milky Way. But at the same time, if you now look at a scientist who works at the opposite end of the physical scale, somebody who's working on the nanoscale or so, who's working with nanoparticles, well, two nanoparticles are close to each other if their distance is a couple of nanometers apart, so some small number times 10 to negative 9 would be considered close there, which is a distance that would be ridiculous to consider on an interstellar scale. So in different contexts of physics, of engineering, of science, close to may mean different things. But the same mathematics, calculus, has to describe these kinds of scales and has to work at all of those scales. So we need to have something that is context independent, and that's where the epsilon delta definition comes in. This is a definition, because it is rather technical and we're not used to working with it, that is much maligned, and that quite a few students actually look at with some chagrin. Trust me, if you just work with it a bit and get used to it, it ultimately is not that bad to work with. At the beginning it's a bit of a shock maybe, but you've seen these things before. You've gone from algebra to calculus and from single variable calculus to multivariable calculus, and those are steps that are also not necessarily easy. So we'll walk our way through this here too. Alright, so what do we have? The epsilon delta formulation of the limit of a function is the following. We take a deleted neighborhood of z0, and I typically call those things omega because that's a letter that reminds me of open, so for open sets also. And we let the complex function f be defined on omega, and we say that w0 is the limit of the function f at z0 if and only if, for all epsilon greater than 0, there is a delta greater than 0, so that for all z in omega, so that z minus z0 is smaller than delta, we have that f of z minus w0 absolute value is smaller than epsilon. So this definition is a triple or quadruple punch because it really has these 4 stages that I've listed here. We want to talk about for all epsilon greater than 0. And what does that epsilon do? That epsilon controls the distance between f of z and w0. So that epsilon, remember we're always thinking epsilon is small. We're not going to say what small is, but that controls that f of z must be close to w0. In mathematics, it'll be any positive number, so it can be 10 to the negative 59, which is something, if you work it in meters, is something that is totally inaccessible to physics and to measurement. For quantum physicists, epsilons will be on the order of, I don't know, 10 to the negative 10 or so. And for people who work in interstellar scales, it may be on the order of light seconds or so, which is substantially larger if you actually need to put a context to it. But as I said, the mathematics must be context independent, and so this must work for all positive numbers. Okay, second part of this thing is there is a delta greater than 0, and that delta controls the closeness in the input, because the delta says such that for all z, so that z minus z0 is smaller than delta. So for all z sufficiently close to epsilon, sufficiently close to z0, and that's controlled by this delta. And so now we see the closeness, the tolerance, the tolerance level, as I usually call it, is given by the epsilon. The epsilon comes first, and it defines closeness in the image. And then you have to find a delta, and that delta now must be sufficiently small so that the inputs that come from z minus z0 smaller than delta will go into will get close enough to the W0 in the output. So that's how the delta with a z minus z0 smaller than delta encodes this rather non-specific, sufficiently close to z0. Okay, so in pictures this would mean we've got z0 here, we've got f, we've got w0 here, and now we have some tolerance around w0 that is given by the distance epsilon. And for this distance epsilon, we must find a delta, a threshold delta, so that as soon as z enters this threshold, as soon as z minus z0 is smaller than epsilon, every z in here gets mapped into this little disk around w0. The notation is the same as in calculus. The limit as z goes to z0 of f of z is w0. Okay, now we're going to start doing some proofs with these things, and the first standard proof really is to prove that the limit is unique. So theorem, if we have deleted a neighborhood of z0, and the complex function f is defined on that deleted neighborhood, and if w0 and w1 are limits of f at z0, then w0 is equal to w1. Note that if you want to go back to the previous panel, I actually did not talk about the limit. I've said w0 is called limit. The limit would already indicate the connotation that the limit is unique, but we don't know that at this stage. So suppose there really are two numbers, w0 and w1, that satisfy the property of the limit. We claim that then those two numbers must be the same. How do you prove that? Well, it's a proof by contradiction, or well, actually it's not really a proof by contradiction. It's a proof up to epsilon. We let epsilon be greater than 0. This is something that's actually fairly typical for an analysis proof. A lot of analysis proofs just start with picking an epsilon greater than 0. Well, that's not that bad. Part after that is usually where it gets hard. Well, okay, so we pick any epsilon greater than 0. Because w0 and w1 are limits of f at z0, there must first of all be a delta 0, so that for all z minus z0 smaller delta 0, we have that f of z minus w0 is smaller than epsilon over 2. That comes from the definition, and if that works, the definition works for all epsilon, then it also works for an epsilon prime that is epsilon over 2. Don't worry about why I chose the epsilon over 2. We will see that at the end of the proof, and we'll talk about it some more then. But basically, this is something that comes straight out of the definition. Similarly, there's a delta 1, so that for all z minus z0 smaller delta 1, we have f of z minus w1 is smaller than epsilon over 2. Again, straightforward application of the fact that w1 is a limit of f at z0. Okay, now I want to choose a z so that z minus z0 is smaller than the minimum of delta 0 and delta 1. Well then, w0 minus w1, that absolute value, well that's equal to, remember there are only two tricks in mathematics, adding 0 and multiplying by 1. And what we're doing here is we're adding 0, right? We subtracted f of z and added f of z. How can you think of that? Well, that's the kind of thing where the experience comes in right now. As I mentioned before in some other proofs, let's just verify that it works. Let's understand that this really is a watertight argument. Well, now we're going to use the triangular inequality. And we know that the absolute value of something is always less than or equal than what we get if we take the absolute values of the individual pieces. And so here this is therefore smaller or equal than w0 minus f of 0 plus f of z minus w1. Okay, but now remember, z minus z0 is smaller than delta 0 and smaller than delta 1, so we know that the first absolute value is smaller than epsilon over 2, and the second one also. So this means this guy is smaller than epsilon over 2, this guy is smaller than epsilon over 2, which is epsilon. And because epsilon greater than 0 was arbitrary, well, that means that the difference between w0 and w1 is arbitrarily small. But the only way that can happen is if those two numbers are in fact one and the same number. And that's the end of the proof. Wow. Okay, first of all, go through it again if necessary. Make sure you understand all the steps, and make sure that you understand that this argument is watertight, that there are no gaps in the reasoning. That is the big thing about a mathematical proof. A mathematical proof is an unassailable guarantee that the result that has been proved will be true no matter what. Once we've got that, and if necessary, hit pause, rerun the presentation, read it one more time in the book. Now let's take a look at how you get this idea. The main idea in analysis, and also in complex analysis, therefore, is that you always want to control differences and make them small. So, for example, if I want to show an analysis that two numbers are equal, it is quite a standard approach to just show that the absolute value of the difference of these two numbers is smaller than any epsilon. So this is something that somebody must have told you at some point in time. I just did. That doesn't mean just because somebody told you, you'll automatically remember it right away when you need it. There are too many other proof methods out there. But it's worth to file away in memory for future use. And so with this idea that we want to prove that W0 minus W1 is smaller than epsilon, I have to start thinking about, well, what can I control? What can I make small? Okay, low disk space. Well, let me get a pause here real quick. Okay, I've fixed my low disk space. I think we'll get through this presentation now. Okay, where were we? We had to control the difference between W0 and W1. I want to make that smaller than epsilon because that's just one of the standard ways to prove that two numbers are equal. Okay, well, that's what I want. Now, how can I get that? What can I control? Well, because of W0 and W1 being limits, the things that I can control is the distance between W0 and f of z for z close to z0, and the distance between W1 and f of z for z close to z0. So that means it becomes actually fairly natural to shift in an f of z here in this fashion to make this small. And well, then I just have to make sure that I can find the f of z's so that these differences are small, and I can find those, but the deltas for the different z's may be different, which is why I have to choose the z that I use in this proof actually so that z minus z0 absolute value is smaller than the minimum of delta 0 and delta 1. So if you just listen to what I've just said, then you realize that this proof actually was conceived in exactly the opposite direction in which it was presented. And that is fairly common in these kinds of proofs. You get your idea from the final estimate that you want to write down, and once you have that, you start thinking about what you need in order to make all the steps in the estimate work out, and that's when you write down this header. Sometimes people then even want you to submit your scratch work. We're going to see a proof with that scratch work also, but basically the good thing, or the thing to remember in these kinds of proofs typically is that your final estimates actually drive everything, but you still want to write them out in linear fashion because that's the way in which you can make absolutely sure that, or that's the best way to make sure that you haven't made any mistakes. Okay, let's move on. Let's take an example. Let's prove that the limit as z goes to I of z squared is -1. Now, this is something that shouldn't be too surprising because after all, I squared is -1 also. So what we're actually proving here is that the function z squared is continuous at I, but it's instructive to go through the steps. And so here, let's talk about this in terms of first thinking about scratch work and then writing down the proof with the epsilons and the deltas and everything else. So what I need to have at the end of the proof is I need that epsilon is greater than z squared minus -1 absolute value. Well, that's z squared plus 1 absolute value. And if I factor that, that's z plus I absolute value times z minus I. But the z minus I, that's something I can control because remember, z goes to I. So this guy is going to get small. The z plus I, the only thing that could make our argument go wrong is that the z plus I could get large. Well, come on, if z is close to I, then z plus I ought to be smaller than 3 or something like that. And, well, so that ought to work. So the term z minus I can be made small as z goes to I, and the term z plus I will be bounded as z goes to I. So this ought to work. I just make z minus I smaller than something that will make my final estimates work out. And so here's the clean argument. We let epsilon be greater than 0, and we choose delta, and this is sometimes the mysterious part also in analysis proofs. How on earth did people get the idea to choose delta to be the minimum of epsilon thirds and 1? Well, we'll see that in just a second. I've already mentioned that I can make this thing small, but it's multiplied by something, and I said, well, I can probably make this thing smaller than 3. So that means this epsilon thirds is kind of motivated by what I've set up here. We'll see in the end, it's just chosen so that the final estimates work out. Because now for all z minus I smaller, for all z, so that z minus I is smaller than delta, we have that z squared minus negative 1 is z squared plus 1 absolute value, which is z plus I absolute value, z minus I absolute value. You notice here, and this is not an accident, all the stuff from the scratch work up here is coming back down here. And that now, here we're using the triangular inequality. Z plus I is z minus I plus 2i. And by triangular inequality, that's smaller than z minus I plus 2i absolute value. Because I need some way to control the z plus I absolute value. And using the triangular inequality, that's another thing. That's another skill that you pick up with enough practice. And then we've got the multiplication with z minus I here. And now I know this thing is smaller than 3 because z2i absolute value, that's 2. And z minus I absolute value, well, that's smaller or equal than 1 because it's smaller than delta, and delta was smaller or equal than 1. So that's smaller or equal than 2 plus 1, which is 3, or strictly smaller, in fact, than 3. And z minus I is smaller than epsilon thirds, and 3 times epsilon thirds, that works out really pretty. That gives the epsilon. I typically like to write my proofs in such a way that really at the end I have an epsilon, because sometimes if you do a sufficiently complicated estimate, you might end up with something times epsilon, and that something might be, in fact, somehow in a hidden way depend on epsilon and make actually everything go wrong. But this one is a correct proof. And so, as you can see, this is another way to write down these proofs. If you go back to your calculus text on a section that, let me admit it, in many calculus classes, including very often my own, that section is actually skipped. They tell you a lot about these epsilon delta proofs, and some authors even insist that you first write down the scratch work and then write down the clean argument. There is some merit to that, and rather than getting into a quarrel about philosophy, let me simply state that I personally don't need to see the scratch work. The main thing I need to see is a correct proof. And the way I would typically recommend to do that is that you first work out the final estimate, and sometimes that estimate looks so good that you might as well have it on the second half of a page, and then you write the header on the first half of the page. That way you get the benefit of doing the scratch work without having to just copy everything back down. Because if we want to be completely honest, I mean, this part here is just copied down here. This is where the main idea is, and you don't get any better idea out of it by copying it down again. And typically when there is a lot to write, even though you want to mindfully write this down and think about every step one more time, if I've got a lot of stuff to write, I just want to have it over with. And so there are various ways to do that. On the other hand, if it helps you to first do the scratch work and then the clean argument, by all means, go ahead and do it. This stuff is hard, and we want to get it right. That's the main thing. All right, another example. I want to show that the limit as z goes to 0 of z bar over z does not exist. Well, okay, so what does it mean that limit does not exist? Basically what that means is that as we get close to 0, this thing doesn't stabilize near one particular number. And so if I can show that I can find arbitrarily close to 0 different outputs that are so that the difference of these outputs cannot be made smaller than epsilon, then I can prove that the limit does not exist. So take z equals x plus I, y not equal to 0. and choose y equals lambda x, and we'll see why that is the case again in just a second. Then we have that z bar over z is x minus iy over x plus iy, which is x minus I lambda x, x plus I lambda x. And I can factor out the x here to get x times 1 minus I lambda, x times 1 plus I lambda. And that's just 1 minus I lambda over 1 plus I lambda. What's so great about that? Well, z equals x plus iy, that's any number that we ultimately want to be close to 0, but lambda is a constant. So the way this idea must have come about somehow is that I wanted to get rid of the dependence on x and y. And the way to do that is, first of all, you make y some function of x, and then you factor out the x and hope that it cancels, and it does. Why does that help me show that the limit doesn't exist? Well, the last term here is independent of z. And so no matter how small I chose my delta, so that z absolute value is smaller than delta, with lambda equals plus minus 1, the output will be 1 minus I over y plus I, for lambda equals 1, and 1 plus I over 1 minus I, for lambda equals minus 1. And these two numbers will not be close to any single number w0 because these two numbers are a definite finite distance apart. And now let's remember that the epsilon had to be any number greater than 0, which means it doesn't matter if we think that these two outputs that I've just mentioned are close together or not. They're not closer together than any epsilon greater than 0, and that means that this function does not stabilize near the origin, and that means that the limit does not exist. Okay, now we've got some theorems about limits, and these theorems are supposed to help us in, of course, computing limits. So let omega be a deleted neighborhood of z0, which is again x0 plus iy0, and take the complex function f equals u plus iv, defined on omega. Then the limit of f is u0 plus iv0, if and only if the limit as y goes to x0, y0 of u is u0, and the limit of v as xy goes to x0, y0 is v0. This theorem basically allows us to reduce complex limits, which would have a real part and an imaginary part, to real limits. And that means that if we choose to do so, we can take a complex limit, puzzle it apart into real and imaginary parts, and use all the things that we know about limits of functions of a real variable or of two real variables, which is something that is briefly touched upon in multivariable calculus. And as you do that, you can then compute limits a little bit more easily. Okay, what's the proof? Well, let's first take a function so that the limit as z goes to z0 of f of z is u0 plus iv0, and we let epsilon be greater than 0. Well, then there is a delta greater than 0, so that for z minus z0 smaller than delta, we have that f of z minus the limit u0 plus iv0 is smaller than epsilon. That's just straight from the definition of the limit. Well, hence, for xy minus x0, y0, remember the difference in the real picture is the same as the difference of the absolute values z minus z0. We have, therefore, that xy minus x0, y0 is equal to z minus z0, which is smaller than delta. And that means that u minus u0 is smaller than f of z minus u0 plus iv0, because this absolute value is greater because it just attaches the difference of the imaginary parts there also as squares inside the square root. And that was smaller than epsilon by what we were able to assume, right? Moreover, same story goes for v. This difference here is smaller than this difference over here, because on this right-hand side, we've got the square root of the square of u minus u0 plus the square of v minus v0. So that thing is bigger. And again, by what we had been allowed to assume, this difference is smaller than epsilon. And so basically that means that the limit of u as xy approaches x0, y0 is u0, and the limit of v as xy approaches x0, y0 is v0 because there is a delta so that when y minus x0, y0 is smaller than delta, we have that u minus u0 here is smaller than epsilon, and v minus v0 is smaller than epsilon, also in absolute value. Okay, conversely, well, let's let the limit of u be u0, and let's let the limit of v be v0. And we, of course, let epsilon be greater than 0. Then there is a delta greater than 0, so that when xy minus x0, y0 is smaller than delta, we have u of xy minus u0 smaller than epsilon halves. Well, we now have to piece f together from u and v, right? So it apparently makes sense that we need an epsilon halves there somewhere. And we also can have that v minus v0 is smaller than epsilon halves. Remember, in the first proof we did for the uniqueness of the limits, I worked with a delta 0 and a delta 1 and then chose the minimum. Well, this delta is basically the minimum of a delta 0 or a delta u for u and a delta v for v. Okay, hence for xy minus x0, y0 smaller than delta, we have the following. F of z minus u0 plus iv0. Well, that's u of xy plus ivxy minus u0 plus iv0, which is smaller or equal, well, that's u minus u0 plus v minus v0, and again we've used our best friend, the triangular inequality. And we know the first one is smaller than epsilon halves, the second one is smaller than epsilon halves, and that's epsilon. And so that means we have proved, conversely, that if the limit of u is u0 and the limit of v is v0, then the limit of f is u0 plus iv0, because again, for any epsilon greater than 0, we have found that delta greater than 0, so that xy minus x0, y0 smaller delta implies that f of z minus u0 plus iv0, and remember this is just z minus z0, is smaller than epsilon. Okay, so let's take a break right here, because I think the next proof is actually quite lengthy. And this presentation also has gone quite a long time, and I'm running the risk, or at least I'm getting worried about maybe touching the wrong button and erasing the file that is being created here, which I wouldn't want to happen after 45 minutes of talking. Plus, you're probably rather tired of listening to me at this stage. Let's take a quick break. Go ahead and read the section on the limits. Take a look at some of the homework problems. See if you can prove a couple of results about certain functions having certain limits, and then we'll start talking about the limit theorem as we get back in the next video. Until then.